Hello students, by this module let us study about Bohr's model of an atom. Prior to Bohr, there were a number of scientists who were working on the structure of atom. Rutherford was one of them and his model was close to Bohr's model of an atom. In fact, Niels Bohr had helped to overcome the problem in the Rutherford model of an atom. Rutherford model of an atom has a major drawback, that is, it could not explain the stability of an atom. It showed that electrons in an atom revolve around the positively charged center called nucleus. However, later it was found that any particle in a circular motion would undergo acceleration and thus would lose energy. So, the electron would take a spiral path and finally fall into the nucleus and the atom would collapse. But this does not take place in reality. Bohr said that electrons do not revolve around the nucleus, but their energy remains fixed. He explained that the energy of electrons remain fixed because they are restricted to some fixed orbits. Each of these orbits is at fixed distance from the nucleus and is associated with fixed amount of energy. These orbits with fixed energy are known as discrete orbits or energy levels. The energy levels are represented by letters like K, L, M, N or numbers 1, 2, 3, 4 starting from the center. So, the final model of Niels Bohr is similar to the Rutherford model of an atom, which states that atom consists of positively charged center around which the electrons revolve. The only difference was that in the Bohr's model, electrons revolve around the nucleus in the fixed orbit with the fixed energy. For his work on structure of atom, he got a Nobel Prize in 1922. Bohr's model for hydrogen atom. Bohr's model of an atom is based upon quantum theory of radiations. Main points of this model are: the electrons in an atom revolve around the nucleus only in certain selected circular orbits. These orbits are associated with definite energies and are called as energy shells or energy levels. These are numbered as 1, 2, 3, 4, etc. or designated as K, L, M, N, etc. shells. Only those orbits are permitted in which the angular momentum of the electron is a whole number multiplied by h by 2 pi, where h is the Planck's constant. That is, angular momentum of the electron mvr is equal to nh by 2 pi, where n is equal to 1, 2, 3. Where m is the mass of the electron, v is the velocity of the electron and r is the radius of the orbit. In other words, angular momentum of electron in an atom is quantized. As long as electron remains in a particular orbit, it does not lose or gain energy. This means that energy of an electron in a particular orbit remains constant. That is why these orbits are called as stationary states or stationary orbits. When energy from some external source is applied to the electron, it may jump to some higher energy level by absorbing a definite amount of energy equal to the difference in energy between the two energy levels. When electrons jump back to the lower energy level, it radiates some amount of energy in the form of photon of radiation. Delta is equal to E2 minus E1, that is equal to h nu, where nu is equal to E2 minus E1 by h, where nu is the frequency of the emitted radiation. Quantization of energy and Bohr's model. According to Bohr's model, energy of the electron in an atom is quantized. Quantization means that a quantity cannot vary continuously to have any arbitrary value but can change only discontinuously to have some specific values. To illustrate this point, let us consider a simple example. Suppose a person moves down a staircase, then energy of a person changes discontinuously and he can have only a certain definite values of energy corresponding to the energies of various steps. Energy of the person is quantized. On the other hand, a person moves down a ramp, energy changes continuously and he can have any value of energy corresponding to any point on the ramp. Energy in this case is not quantized. So, according to Bohrs model, energy of an electron in an atom is quantized. The main success of Bohrs models are: Bohrs model could explain the stability of an atom. Bohr's theory helped in calculating energy of an electron in a particular orbit of hydrogen. The expression is En is equal to minus k squared 2 pi square m e to the power 4 divided by n square into h square, where m is the mass of the electron, E is the charge of the electron, h Planck's constant and k is the Coulomb's law constant. On substituting the values of these constants, we get En is equal to minus 1312 divided by n square kj per mole. Bohr gives an expression for the radius of an orbit in hydrogen atom. Rn is equal to n squared into h square divided by 4 pi square km e square. Rn is equal to n square into 0.529 into 10 to the power minus 10 meter. That is, Rn is equal to n square into 0.529 Armstrong unit. Thus, as n increases, the radius of the orbit increases. The radius of the first orbit of hydrogen is equal to 0.529 Armstrong. This is also known as Bohr radius. Limitations of Bohr's atom model.